invitation, the opportunity to speak here. I've learned a lot already. So let's see. So in the first talk, we went through this stuff. So let me say again, like as with the last talk, this is a description of joint work with a lot of people, depending on ideas of a lot of people, some of whom are listed here. So let me just very briefly, I'll show you these slides to jog your memory maybe very slightly. But then just to recap a little bit, what I described last time, at least, the mathematical content of it was a kind of conjectural recipe for building some hyperkähler manifolds, specifically hyperkähler manifolds where the hyperkähler structure is a structure on the total space of a complex integrable system. Some particular ones, and the idea was that the way you would make the hyperkähler structure was to construct, rather than constructing the hyperkähler metric directly, you would construct the twistor space of the hyperkähler manifold. And the idea, the key thing in the construction was, okay, so the twistor space ultimately is going to be a complex manifold with this, complicated fiber-wise holomorphic symplectic structure. But the way you think of it is you first say, okay, well, just in the C infinity world, what it is M cross CP1. So I got my real manifold M on which I want to put this structure. I just build the C infinity manifold M cross CP1. And then the way we equip it with this fiber-wise holomorphic symplectic structure was essentially to, even though this space is supposed to be something complicated, the idea was to locally identify it with just a holomorphic symplectic torus, C star to the n. And that torus came to us as the C star valued characters of this lattice gamma. So the idea was to construct a map from M to this C star to the n. And the map depends on the coordinate zeta. So for each fixed zeta, you're mapping M to a torus, then you're doing that in a way that depends on zeta, the twistor parameter. And so in that way, you're supposed to get a kind of C star family of complex symplectic structures just by pulling them back from the torus. So the key thing was to construct this zeta-dependent map from your manifold to the torus. That's what we're trying to do, and then pull back all the structure from the very simple structure of the torus. Now, the way that I said that we want to construct that map was by some seemingly very complicated procedure. Well, it is a complicated procedure. So it's the solution of some Riemann-Hilbert problem. And so we specified a bunch of properties that it was supposed to have. So the properties were, first of all, it has to blow up as zeta goes to 0, but it has to blow up in some very specific way. It has to go asymptotically like zeta inverse. So we had this parameter R, and the central charge number is Z gamma. And so the leading asymptotics of the thing have to go like zeta inverse to R Z gamma. And then there were subleading terms that depended on where you are in the torus fiber of M. So this X is supposed to have those asymptotics. Then it was supposed to have a kind of complicated analytic structure in the zeta plane. So it wasn't just a holomorphic function of zeta, but rather it had this kind of piecewise analytic structure where if you fix a point of M and just look at how it depends on zeta, it would jump at various rays in the zeta plane. And those jumps were given by some holomorphic symplectomorphisms of the torus. Symplectomorphism disappeared from my slide, but anyway, that's fine. The formula, maybe the formula doesn't matter. The symplectomorphism was completely determined by these BPS integers, BPS counts. And then the last property that it had was some symmetry under the antipodal map, under zeta goes to the antipodal point, -1 over zeta bar. Okay, so that was the story that I told you. And then there are lots of interesting questions about whether you can or can't solve that Riemann-Hilbert problem in practice. There's a fundamental question which one might ask, and which a few people did ask, which is why would you ever do that? I mean, I told you that we do this thing and it seems to work, but it seems to work in some very specific examples. But you guys, why would you ever, what would lead you to do that? So, okay, so I want to give at least some partial answer. This behavior doesn't come out of nowhere. This is a kind of thing that's been seen before. And in particular, this kind of analytic behavior, where you have a thing that blows up like exponential of something over zeta as zeta goes to 0, and which jumps as you move from one sector to another, is exactly the characteristic behavior that you see in the theory of ordinary differential equations with an irregular singularity. So imagine for a second that you were studying an ordinary differential equation in the zeta variable, which has this form. So zeta d by d zeta of x is equal to, and then some 3-term expression with a pole, like 1 over zeta times something plus zeta times something. And think of each of those a's as just being some matrices. So there's just like some matrix ODE in the zeta plane. So suppose you had an equation of that type, just for n by n matrices. And suppose that it has some reality property where the A1 is the conjugate of A minus. I guess A naught should be regular. So then you can ask, what's the behavior? How should I think about the solutions of that equation? And it turns out that there's a kind of canonical way of describing the solutions. There's a way of constructing a kind of canonical fundamental solution which has properties very similar to what we wrote for this x of zeta. And in that case, the jumping behavior that I talked about at the raise, the jumps are, instead of being given by some complicated symplectomorphism of a torus, they're just given by unipotent matrices in GLN. They're called the Stokes matrices. So this kind of behavior, looking for an object like this, doesn't come completely out of nowhere. And in fact, exactly this situation has come up in supersymmetric quantum field theory before. So my context was supposed to be the context of n equals 2 supersymmetric field theories in 4 dimensions. There's a simpler thing which had been studied before by people including Chakotay-Baffa and Dubrovin, where you literally need a differential equation over CP1 with this form. And there was also a correspondence between the entries in the Stokes matrices and the BPS 1 particle states. And in fact, the way you would construct some solutions of the equation was exactly by solving an integral equation, which is like the integral equation that I wrote last time. So that's my first attempt at explaining why this behavior looks natural. It would be natural if you had some differential equation in the zeta plane. Okay, so then, well, is there or isn't there some differential equation like that in the story of 4-dimensional n equals 2 theories? Well, okay, so I claim the answer is yes. But it's an infinite dimensional version of the story of the previous slide. So in the previous slide, I was talking about equations like this that are valued in finite n by n matrices. To get the analogous equation in the story of canonical coordinates on hyperkähler manifolds. So first of all, instead of considering this x just point by point on the manifold M, I'll consider x on a whole torus fiber. So now it's a function of theta and zeta. And then I want to say that these canonical coordinates that we're writing down are indeed solutions of some differential equation like this, where now the a's are derivatives in the theta direction. So they're valued in the algebra of vector fields on the torus fiber. And so they're valued in this infinite dimensional algebra, acting on the infinite dimensional space of all functions on the torus fiber. And the Stokes matrices are likewise living in an infinite dimensional group. It's the group of symplectomorphisms of the torus, where we wrote down these explicit transformations last time. Okay. Now, okay, so I say there's an equation. So why is there an equation in the zeta direction? So to explain that, let me simplify a little bit by considering this kind of running example that I was looking at throughout the example that I called the A1, A2 example. In that case, we're studying this hyperkähler manifold, which is a moduli space of Higgs bundles, and it has the feature that all of the fibers of the twistor space, except for the fibers over 0 and infinity, all the rest of the fibers are actually isomorphic. They're all isomorphic to just the moduli space of, well, an appropriate moduli space of flat connections in the plane. If you like, that moduli space of flat connections in turn is isomorphic to configurations of 5 points of CP1. If you did the same thing, if you did something similar over a compact curve, it would be the moduli space of representations of the fundamental group. Anyway, this is a feature that moduli spaces of Higgs bundles have. As long as you don't have any residue data at the punctures, they're literally they have this kind of isotropic property where the complex structure of the space is the same for all zeta and C star, and only the fibers at zeta equals 0 and zeta equals infinity are different. So that's the case in this example. All the fibers of the twistor space are the same except for 0 and infinity. And another way of saying that, kind of geometric way of saying that, is that there's a holomorphic C star action on the twistor space that just implements that isomorphism. In other words, just identify the part of the twistor space away from 0 at infinity with C star cross M flat, and then you just have the trivial C star action on that space. Okay, so there's a holomorphic C star action on the twistor space. And so then you can just, we're studying functions on the twistor space. And so you can just look for functions that are constant along that flow, and that gives you some ordinary differential equation. And from that point of view, it sounds like it would be, when you describe it in those coordinates, it sounds very trivial. But when you describe it in the coordinates that you naturally have on M thought of as just a fixed C infinity manifold, it looks relatively non-trivial. And that's the ODE. That's the ODE that we're looking at. That's why this equation is there. And so in more general examples, we could do the same thing, but we have to throw in some additional torus directions to take care of the flow of some other parameters. So in more general examples, the fibers are not quite isomorphic. They're all moduli spaces of flat connections, but moduli spaces of flat connections with different data at the singularities. But that's not a big deal. You can take care of that. Okay, so that tells you that there's going to be some ODE in the zeta direction in this story. Then there's the question, why is it of the particular form that I wrote? So I said that you know, the behavior that we were finding in this, the behavior that we're looking for in this Riemann-Hilbert problem, it's characteristic of ODEs with this very particular form. So why do we have an ODE in the zeta direction of this particular form? Well, so to see that, you have to do a little bit of work. Essentially, what you have to do is you have to first write down the C star action in the most obvious way. Then you have to kind of rectify it a little bit. So these A's are supposed to be derivatives just along the torus fibers. And when you write down the C star action, you have derivatives in all different directions. But then what you can do is, because the functions are supposed to be holomorphic, you can use the Cauchy-Riemann equations to eliminate derivatives in the base directions in favor of derivatives along the torus fibers. And after you do that, you see that the equation has this form. And in fact, because you also have a kind of explicit description of what the space looks like in complex structure 0. That's the complex interval system that you originally started with. So that actually gives you a formula for what A-1 and A1 will be. And that's what determines the shape of the leading asymptotics. Okay, all this is just to say that this prescription, this Riemann-Hilbert problem, doesn't completely come out of nowhere. It comes first from these analogies with the finite dimensional case, this work of Chakotay-Vafa and Dubrovin, where things were better understood. And second, it comes from the fact that there is also in our story a natural kind of C-star action in the picture. And that C-star action gives you a differential equation in the zeta direction. The last thing you might wonder is, why are the Stokes factors going to be of the particular form that we wrote? So I just sketched for you how you see that the asymptotic behavior is what I said. But in writing down this Riemann-Hilbert problem, you have to write down the asymptotic behavior, and you also have to write down the Stokes factors. So there's a question: why would you guess that the Stokes factors would be of this particular form, determined by these BPS invariants, omega gamma? Well, okay, so there's a few different answers for that. So one answer is that those automorphisms have appeared in a different context. They appeared in the context of the Kontsevich-Stolpermann wall crossing formula for Donaldson-Thomas invariants. And so if we identify those automorphisms as the Stokes factors for our connection, and then if we extend the connection, so far I just talked about a connection or a differential equation in the zeta direction, which you might say a connection just over CP1, the CP1 parameterized by the twistor parameter zeta. We can also extend that to a connection over CP1 cross the base of the complex integrable system. The extension in the horizontal directions and the directions along the base just comes from solving the Cauchy-Riemann equation. So it's a connection on the space of functions. So the condition of being flat in the B direction is just a condition of being a holomorphic function. So in that way, you get a connection not just on CP1, but over CP1 cross B. And then if you look at the connections restricted to just CP1 at different points of B, the fact that they all fit together into a single flat connection means that the Stokes factors have to be related to each other by this isostokes deformation. It's kind of the irregular singularity version of isomonodromy, saying that the monodromy is invariant. And if you look at it in that way, the isostokes deformation gives you some constraint on how these omega of gammas, how these numbers omega of gamma can change. And that change is then reproduces how Kontsevich-Stolpermann said they were supposed to change, the Kontsevich-Stolpermann wall crossing formula. And that mechanism was identified by Bridgeland and Toledano-Laredo in very closely related contexts. So they had this idea that the wall crossing formula kind of comes from isostokes deformation. So that idea plugs perfectly into this this problem. Okay, so that's one way that we might guess these Stokes factors. Another way is that after the fact, once you've made this conjecture, you can look at the examples where we feel like we understand things. Particularly, you can look at these examples of class S theories, the examples that had to do with SL2 Higgs bundles over a curve. And in those examples, you can show directly that the Stokes factors are of the form of this form. And that essentially goes back to the exact WKB theory. And so I think in that context, this formula is sometimes called the Delabert-Dillinger-Pham formula. Okay. And the fact that those, okay. And then another answer is that there's a kind of physics reason for it. So these X gammas, they have a physical interpretation as vacuum expectation values of line defects. And that leads to this formula for the job. Okay, so none of what I just said is is fully rigorous mathematics, but they are all kind of motivations for why you might write down this Riemann-Hilbert problem. So Okay, I just wanted to try to explain that it doesn't come completely anymore. Okay. So, okay, now I want to shift a little bit and talk just in order to connect with some of the other talks at this conference. I wanted to briefly talk about this conformal limit. So the Riemann-Hilbert problem, the way I formulated it, it involved two parameters. It involved the parameter zeta, which was keeping track of the complex structures, so coordinate along the twistor line. And then it involved this real number, R, which essentially just had the role of rescaling the central charges. And so in particular, the Riemann-Hilbert problem involved writing down these leading asymptotics that used R and zeta. And if you just look at what happens as zeta goes to 0, those two numbers don't appear individually, but rather it's the combination R over zeta that appears. And so as far as those leading asymptotics go, it looks sensible to take a kind of limit where you take the parameter R goes to 0. So you're sort of, you're rescaling the central charges to be very close to 0. At the same time, you're taking the parameter zeta goes to 0. So you're looking very near the origin of the twistor space. So very near the north pole of the twistor space. You're kind of zooming in there. You take them both to 0, but you take them to 0 in such a way that their ratio is fixed. But I have a typo here. Sorry, it should be R over zeta is 1 over h bar. So that's some number in C star. And so formally, then you can write down a different Riemann-Hilbert problem where the asymptotics now are exponential of z over h bar plus I theta. But now the asymptotics as h bar goes to infinity are not as clear. So we destroy the symmetry between z equals 0 and z equals infinity. And so this version of the Riemann-Hilbert problem, where we fix the asymptotics like this at 0. We don't impose a reality condition, and then there's a problem of how to fix the asymptotics at infinity. And so you can impose, as Tom has formulated it, you have to impose some kind of moderate growth condition. In simple examples like this A1, A2 example, you can actually impose a condition that the function just go to constants at infinity. So here's that's a kind of simplified Riemann-Hilbert problem, which you can also try to solve. So Tom and the collaborators have discussed how to solve it in some examples, particularly in these kind of uncoupled examples, following one example that was done by Gaiotto. And in contrast to this case where you have this complicated reality condition to impose, we don't have the reality condition. You can write down some pretty explicit functions. They have some solutions just in terms of like gamma functions and other special functions. So what's the meaning of this conformal limit in terms of these theories of class S? So I told you before that in the theories of class S that have to do with a punctured Riemann surface, that these functions that are the solution of the Riemann-Hilbert problem, they're supposed to be interpreted as giving monodromy or Stokes data of some flat connections on the Riemann surface. And those flat connections are in the form that I wrote here. So if you think of the flat connection as giving kind of a matrix ordinary differential equation, you're trying to find the monodromy of that ordinary differential equation. But the equation is pretty hard to write down. Like if you ask me what's that equation, even in the very simplest A1, A2 example, I say, okay, you solve this Riemann-Hilbert problem and you get the monodromy of some differential equation. And then you say, great, what differential equation? And then I have to say to you, well, to get the differential equation, you first have to solve this PDE, this elliptic PDE in the plane with some complicated boundary conditions. I have to do that before I can even write down the differential equation that I'm studying here. And so Okay, that's still interesting. For the hyperkähler geometry of the Hitchens system, that's actually what you want. But you know, in the theory of flat connections, it looks maybe like an unpleasantly complicated thing to be learning about. In the conformal limit, the story becomes simpler. So so then we get functions of a parameter h bar, and at least one way of getting solutions of the conformal limit problem is to write down invariants of equations which you actually can write down. So, for example, in the A1 A2 case, the relevant equation is literally just this Schrodinger equation with cubic potential in the complex plane. Literally the equation that I wrote at the bottom. And then you're studying some kind of Stokes invariance of that equation. Or if you don't like irregular singularities, you can do it on like a 4-punctured sphere, and then you're studying the actual ordinary monodromy of a kind of Schrodinger equation on the 4-punctured sphere. Now, one of the tricky things, so as I said, we don't have a lot of theorems about the solutions of this Riemann-Hilbert problem. And so I believe the situation here is that it is known, thanks to work of Bridgeland, Allegretti, and collaborators, it is known that the monodromy data of that equation actually do give a solution of the Riemann-Hilbert problem. What's not known is any kind of uniqueness, I think. I mean, I think you might think that there's tons of other solutions. But one interesting and sort of encouraging thing is, so I told you in the other case that you can find solutions by numerically by solving integral equations. And you can do that here too. So, so you would just shut your eyes and write down an integral equation whose solutions would be solutions of this Riemann-Hilbert problem, and then just try solving it by iteration. And sure enough, that works, and it produces the monodromy data of this particular family of Schrodinger equations. So there, we don't know exactly. We don't know why it works, but it does in fact work. And that's been done, that kind of thing has been done for a long time, actually, by physicists studying this thing called the ODE-IM correspondence. And then recently, in exactly this context, I did it with David Dumas in this example and a few other examples. Okay. Okay, so that's about all I wanted to say about the conformal limit. I guess the two kind of takeaways are that the conformal limit is related to problems that are kind of in some ways easier to think about. On the other hand, the Riemann-Hilbert problem itself seems, if anything, to be harder than the Riemann-Hilbert problem in the with the real symmetry. So the convergence is much worse, much less obvious. Nevertheless, in some cases it works, but okay, so that's the kind of trade-off. Okay, so now I want to do the other thing that I promised, which is to talk about the extension of this story that involves hyperholomorphic bundles. So let me again say where we are. So we've been talking about studying a hyperkähler manifold through constructing the complex symplectic structures on its twistor space. Now I want to consider a little extension, and the extension is going to be to construct a whole hyperholomorphic. Actually, mostly I'll talk about just a line bundle, V over M. So what's hyperholomorphic? Let me remind you what a hyperholomorphic bundle even is. So what it is you just have a complex vector bundle over your space. So the underlying space is hyperkähler. You assume you already have that hyperkähler structure in hand. Then you give a complex vector bundle over that space with a metric and a unitary connection. And this connection is supposed to have the kind of miracle property that its curvature is of type 1,1 in all of the different complex structures. So you have one connection, it has this curvature, the curvature is whatever it is. And then you decompose it with respect to the Hodge decomposition of two forms. And it has to be in the intersection of the 1,1 spaces for all of the different complex structures in the hyperkähler family. And one way of thinking about that is, you know, ordinarily, if we have a connection of curvature 1, 1, that's what gives us a that's what gives us a holomorphic line bundle. The holomorphic, sorry, that should say vector bundle. Holomorphic vector bundle. If you just take the del bar part of the connection, del bar squared is 0, provided that the 0, 2 part of the curvature vanishes. So this condition guarantees that this that taking the del bar part of this connection gives you a holomorphic structure for every zeta. So it gives you a CP1 family of holomorphic structures on this bundle, all coming from this single unitary connection. Okay, so that's what a hyperholomorphic bundle is. And so it's kind of like an instanton. In fact, in dimension 4, this is literally the condition of being a Yang-Mills instanton. Like if you were on like R4, R4 is an example of a hyperkähler space, and then this equation would just be the equation of a Yang-Mills instanton. So a hyperholomorphic bundle you should think of as some generalization of Yang-Mills instantons to hyperkähler spaces of arbitrary dimension. Okay, so that's the kind of thing that we're talking about. Okay, and so now, so I didn't make notes for this part, so now I continue on the blackboard. So let's take that away.
Do these complex structure need to satisfy some compatibility?
You mean the different holomorphic structures on the bundle itself?
Sorry, yeah, holomorphic structures on the bundle.
Well, they all have to come from the same unitary connection. So I don't know if that implies any compatibility between them exactly. Well, for example, I guess it means that you know, the one that you have in a complex structure is kind of the opposite of the one that you have in the opposite complex structure in some sense. But I don't know if I can express, well, whatever condition follows from the fact that they all come from the same unitary connection.
I think that condition is that they should be trivial on twistor lines.
Oh, that's a reformulation. Yeah, yeah. So if you describe it in twistor space, right. So that's one of the next things I was going to say. So let me, I guess I'll just say it now since you mentioned. So so there's a fact. Hyperholomorphic vector bundles over the hyperkähler space M is equivalent to holomorphic vector bundles over the twistor space Z of M, but satisfying a condition which is so let's call the holomorphic vector bundle over the twistor space E, such that E restricted to each twistor line is holomorphically trivial. So that's a bundle over CP1. The twistor line is a copy of CP1. So you have some holomorphic vector bundle over the twistor space. When you restrict it to each twistor line, it has to be holomorphically trivial. Then there's a kind of correspondence between those objects and hyperholomorphic vector bundles over M. You can kind of imagine how it goes, right? At least one way. If you have a bundle which is trivial over the twistor line, then in space of sections has the same dimension as the rank of the bundle itself, and that space of sections becomes the fiber over the corresponding point of that. Yes. And indeed, the way we construct it kind of morally goes through this correspondence. So we'll construct it kind of over on the twistor space. So okay. So let me describe how to construct a hyperholomorphic line bundle over the moduli spaces that we built in this Riemann-Hilbert story. So so to build the hyperkähler structure on M, the way we did it was we build a map x of zeta from M to a torus. And then we pulled back. So I'm re-saying what I said before. We pulled back holomorphic symplectic structures var pi of zeta in a family. So we have this family of maps to the torus, use them to pull back a family of holomorphic symplectic structures. So now we want to build a hyperholomorphic line bundle over M. What we'll do is we'll build a kind of diagram. So we're just going to extend this to a diagram of bundles over spaces. So we have a map. So before, what we had was this map, x of zeta, t. And now we're going to have just a C infinity line bundle over M. So remember, in this construction, we first think of M as just being a C infinity space, which gets all its structure through the map. So what we'll do is we'll start with a C infinity line bundle over M. And then over the torus, we'll also have some kind of standard simple holomorphic line bundle, which I'll call script DB. And then we'll just lift our maps of tori to maps of tori with line bundles. That means I have to give a map of the line bundles, which covers the map of spaces. And then we'll just pull back So in order to get a hyperholomorphic line bundle, strictly speaking, all I would need is to pull back kind of the holomorphic structure through this map. But in fact, we'll get something a little bit more. So this is one of the interesting things about this, this line bundle is it's not just a hyperholomorphic line bundle. It comes with a connection, a family of connections whose curvature is this family of holomorphic symplectic structures. So we have these holomorphic symplectic forms. And they will actually be realized as the curvature of connections in this family of holomorphic line bundles. So we'll pull back. I'll say it this way: we don't just pull back the holomorphic symplectic form; we pull back the holomorphic connection, A of zeta, connection in this bundle V to a script V to a connection in the bundle ordinary V. So the curvature of this A will be, now, okay, now there's a little technical point, which is saying that I can do this might raise some alarm bells, because it means that the curvature has to be integrally quantized. In order for the holomorphic symplectic form to be the curvature of some line bundle, it has to be integrally quantized. And in the full generality of this story, the curvature is not always integrally quantized. So let me restrict to the case where this flavor lattice is trivial. And then the curvature actually is integrally quantized. And I can literally make a hyperholomorphic line bundle. Otherwise, I have to make something slightly more general, I think. But so let me restrict to that case. So then, how does the construction look? So the C infinity line bundle over M. So that'll be a bundle which, when restricted to each torus fiber, is the standard Heisenberg line bundle. So let me just describe, so there's some standard construction of a line bundle over the torus, which is called the Heisenberg line bundle. And I'll just describe it kind of in local coordinates, in local trivializations. So I guess the fancy way of saying it would be that we take the trivial bundle over the cover of the torus, and then we quotient out by an action of a lattice to produce a bundle on the torus itself. So we could write it. Let's just suppose to write a concrete formula. Let's imagine so mu is literally a 2 torus. So with coordinates say θ1 and θ2. So then the way we'll construct this line bundle is we take the trivial bundle over the universal cover, and then we make an identification. So I'll let psi be the coordinate in the fiber of this bundle. Psi θ1 θ2 gets identified with, so when I shift theta by 2 pi, gets identified with e to the I θ2 divided by 2. And so there's a tricky sign in this, which I don't want to try to talk about. So if we shift θ1 by 2 pi, then the fiber coordinate shifts by e to the I θ2 over 2. And if we shift θ2 by 2 pi, the fiber coordinate shifts by e to the minus I θ1 over 2. And that's the definition of some just, in the C infinity category, some line bundle over the torus, non-trivial line bundle over the torus. And you do a similar thing in higher rank. Just using, here we had the pairing, I was kind of implicitly using the pairing between gamma 1 and gamma 2 equals 1. And in general, you can construct some similar thing using the pairing. So that's the bundle where we're going to put this structure, and then we're going to identify it. We're going to be mapping it to a similar bundle over the complex torus. In fact, it's literally just a complexified version of this. So you write exactly the same formulas, but just replace theta, the coordinates on this real torus in M, replace them with, okay, I'll write psi I, which you can think of as being the log of the coordinates xi that I was using before. I guess with an I should say I, is the log of xi. So okay, so then we have this, so over our C infinity manifold, we have a real line bundle, and over the torus, which is like our model space, over the complex torus, we have this holomorphic line bundle. And now we're gonna, now we want to identify the two. So we want to construct this map psi of zeta to identify the two. And what's the key property that it has to have? Oh yeah, and this one also has a, since I mentioned this connection, let me write the formula for the holomorphic connection. So the connection is just psi1 equals psi2 minus psi2 psi1. That's the connection form. Again, relative to these local trivializations, that's the connection form. So it's curvature, then it's d psi1, d psi2. That's the holomorphic symplectic form on that torus. Up to a factor of, I guess, 4 pi. So I'm going to put 4 pi. Okay. So what are we trying to do? We're trying to make a map. We're trying to lift our map X to a map of bundles. And now the crucial kind of difficulty that you have to overcome is, remember that this map of M to the torus was not analytic. It's only piecewise analytic. And I sort of carefully said, well, the fact that it's piecewise analytic is not a problem because the symplectic form that you want to pull back is analytic, even though X itself is not. But it certainly looks like a problem from the point of view of constructing this map of line bundles. what do we do at the places where this X suddenly jumps? And if you think about it for a little while, what you really need is the following thing. So let's call this patching. So we said there are some places in the parameter space where this X of zeta jumps by this Stokes factor automorphism of the torus, which, okay, in general, it was some complicated product of these Kontsevich-Soilman automorphisms, but let's just write down the most basic one, the Kontsevich-Soilman automorphism that we called K gamma. I'll remind you what that, K gamma. I'll remind you what that automorphism was. It takes the coordinate x mu to x mu times 1 minus x gamma to the pairing of gamma and mu. So that's some concrete automorphism of the torus. And our X will be jumping by some combination of those kind of automorphisms. And what we need is that our map of bundles has to also jump. So what we have to do is we have to lift this map K gamma to a map of bundles. So I described for you some concrete holomorphic vector bundle over the torus, and now we have this this birational automorphism of the torus mapped from the torus to itself, and we need to lift that automorphism also to a automorphism of this bundle. Okay, and if you try to write down such a lift, okay, you discover that there is one, and in fact, not only an automorphism of the line bundle, but even an automorphism of the line bundle with connection. And what it looks like concretely, so there is such an L gamma. And what it looks like written relative to the local trivializations that I've been writing all these formulas in, what it looks like is the exponential of the dilogarithm function, the Rogers dilogarithm function. It's essentially because the dilogarithm function is a kind of generating function for this symplectomorphism. That's what this more or less boils down to. Is the dilogarithm is a Hamiltonian generating function for this symplectomorphism. But concretely,
can I ask a question?
Yes.
Yeah. So is it fair to say that kind of in this construction, you, instead of pulling back this script V line bundle, you actually you take this line bundle that you constructed and you reglue it using these L gammas, and that's what you want to pull back?
That's what you pull back. But of course, that was also kind of true for the, I mean, even for the torus, you might have said the same thing, right? You might have said, well, it's not really a map to the torus. It's a piecewise map to the torus. So what you're really identifying it with is not exactly the torus, but some gluing thing. So it's exactly the same kind of thing here. So roughly this Rogers dilogarithm, just to write a formula, again, up to the kind of tricky signs in the business. What this Rogers dilogarithm is it's the usual dilogarithm function shifted by some more elementary part, something like this. And of course, this function has all kinds of branch problems. I mean, this doesn't look like a single valued function, but the point in writing these formulas, I've always been working relative to a choice, a specific choice of a logarithm of x here. Well, okay, make a long story short, the branch structure works out exactly right so that this formula actually does give you a map between the appropriate line bundles. So each of those line bundles was defined by some complicated transformation law as you shift the log by 2 pi. And the branch structure of the log is exactly right to make it a map between those, between the fiber of V at a point and the fiber over K gamma at that point. So So okay, so so now what we want to do, sorry. So what we want to do is we want to build our map psi of zeta to have the property that it jumps by psi goes to psi times, the exponential of omega of gamma over 2 pi I times the Rogers logarithm of x gamma of zeta at the jumping places, which I remind you were these rays I called L gamma. And so much as in the Riemann-Hilbert problem that we have for the x gammas, we have to impose some asymptotic conditions for psi of zeta as zeta goes to 0 or infinity. So it has to obey some asymptotic conditions as zeta goes to 0 or infinity. So you could say, from the point of view of Sergei's comment, we have to impose some conditions to guarantee that the line bundle that we're getting is actually going to be extend to something that's holomorphically trivial over each twistor CP1. And so it turns out that there is a formula you can write down which does this. And I'll write down the formula just in case it looks familiar to someone and inspires something. So there's kind of an explicit part, and then there's a part that involves integrals. So much like the things that appeared in the integral equation I was writing yesterday. So the explicit part looks like this. And then there's a part that involves integrals. And the part that involves integrals, I'm cheating very slightly. So this is a slightly simplified version of the formula, but I think it's good enough. So there's a sum over all the BPS particles, all the DT invariants, and then some explicit integral that appears, which is there for the purpose of creating these jumps. Oh, I see. I'm using R for two different things. Okay, let's use a scripty R for the Rogers logarithm. So these R's are the ordinary R, but now comes the scripty R. Rogers logarithm of x gamma of zeta prime. Okay, where I have to define the u and w that appeared on the first line. So u is some function on the Coulomb branch, whose derivative is determined in terms of the z's, and w is a function on the torus fiber that's kind of linear in the torus coordinates. So that's not a periodic function, but that's the kind of behavior you need in order to get a map between these two line bundles. Okay, so all this is just to say that there's some explicit formula that you can write down. Involves integrals in the Rogers logarithm. And once you've solved the Riemann-Hilbert problem for the x's, this gives you a lift to construct this hyperholomorphic line bundle. And it doesn't involve any new integral equation. So this is just the integral formula, not an integral equation. And so I should say, very important thing. So this description, so I wrote this description, but the same description, well, a very similar description set up in a slightly different context, but essentially the same thing was discovered by Alexandrov and Persson and Fueling. Okay. Okay, so that's some kind of automatic construction of a hyperholomorphic line bundle, which comes, in some sense, it comes almost for free with this Riemann-Hilbert construction of the spaces. You can just lift it to this construction of a hyperholomorphic line bundle. Okay.
Sorry, may I ask a question?
Yes.
I forgot something. Does this curly R depends on the straight R?
No, it's curly R. Sorry, curly R is just this Rogers-Dye logarithm function.
No, yes, but when you apply it to X gamma.
Well, straight R will appear implicitly in X gamma.
Yes.
So
X
gamma was some complicated function that was obtained by solving the Riemann-Hilbert problem.
Yeah. You're not fixing some R or some. You're not taking a limit for straight.
No, that's
R
right. That's
going
right.
to zero.
So I didn't take the conformal limit here.
Right,
Now you
thanks.
could do the conformal limit of this whole thing, and then yeah. Then you have also a line bundle. Well, actually, I guess if I'm completely honest, I don't exactly know the geometry of the of what you get when you apply the conformal limit to this story. So you can certainly apply the conformal limit to these formulas, and in fact, the psi that you get after taking that limit, if you take theta equals 0, then the psi that you get that way is like a generating function of the locus of Opers. But yeah, maybe it's best to, I think I should stick with what I understand well for this talk. So if you do it away from the conformal limit, then what you're constructing is this hyperholomorphic line bundle. Okay, now I wanted to say, at least briefly, what's the meaning of this line bundle? So in general, I don't think I know, but there's one special case where we can say something about it. So what is the kind of geometric meaning? Well, I guess, sorry, one thing I should say is there's a general construction. There's a general construction of hyperholomorphic line bundles over hyperkähler spaces with a certain kind of U1 symmetry. With a U1 symmetry that rotates the complex structures, which I emphasized earlier is a thing that we have in this situation. So that's due to Hades. And although I haven't proved it, I think that this line bundle is the same one that's constructed by Hades. So one kind of answer would be, well, okay, it's just this thing that comes when you have a space with the U1 symmetry. But I wanted to mention something else. So I want to consider the special case again of the theories of class S of type A1, the one that had to do with the geometry of a Riemann surface. So then M is the moduli space of Higgs bundles over the curve. And there's a nice geometric interpretation of the hyperholomorphic line bundle over that space. So there's a known, in fact, I think it's known to be equal to the one constructed by Hades. So I'll write hyperholomorphic line bundle VH over this space, where over the fiber at 0 and complex structures 8 equals 0, you can identify it. So just as a holomorphic bundle, what it is the pullback of the determinant line, bundle from Bun-G. So a Higgs bundle is in particular a holomorphic bundle. So you can pull back from the moduli space. You can pull back the determinant line bundle from the moduli space of just holomorphic G bundles. G is SL2. But then, since it's hyperholomorphic, you can also look at it in its other complex structures. So in the other complex structures, we're supposed to be getting a bundle over the moduli of flat SL2C connections. Yeah, and then I guess I'll just finish by saying it's the line bundle that comes from classical complex Chern-Simons theory. So there's a topological field theory, a three-dimensional topological field theory which is defined on manifolds with flat connections. That theory is called classical complex Chern-Simons theory. And like any topological field theory of dimension 3, it assigns the vector space to a 2-manifold. In this case, a 2-manifold with flat connection. And that vector space is the fiber of this bundle. And in that context, this construction involving dilogarithms has a kind of natural meaning in terms of the three-dimensional Chern-Simons theory. So that's something I'm working out with Dan Fried, the interpretation of these dilogarithms in terms of three-dimensional Chern-Simons theory. Okay, so yeah, so I guess I'm out of time, right? Yeah, so I guess I better stop there. Thanks.
Thanks a lot, Andy. Are there any questions?
May I ask something? I don't know if you can hear me.
Sure, you can. I'm not sure who you are because I can't find you on my screen. But yes, please do.
Okay. Yeah, thank you, Andy. And I was curious if you can, if there are other examples in which there is a so explicit geometric interpretation of this hyperholomorphic line bundle.
You mean if you took like if you took some other hyperkähler manifold that just has a U1 symmetry? Oh, you mean other examples of n equals 2 theories where we can understand what this thing is?
Okay.
Right. So I guess the only, I mean, you could say something similar for the theories of the. So this was something that had to do with SL2 connections. You could say something similar for SLN connections,
Okay.
and then it's almost surely the parallel story. Although in this work with Dan Fried, we're working at it very explicitly for SL2 and not for others. But the story looks like it's going to be completely parallel for other ones. And in fact, I think so. For this explicit patching construction in terms of dilogarithms, yeah, I think that hasn't been proved yet, but it's almost surely true. On the other hand, there's also a paper of Hitchen where I think he directly identifies this line bundle constructed by Haydes with the Chern-Simons line. Well, he says it is a determinant line bundle, but that's the same thing as the Chern-Simons line bundle. So for that construction, not involving dilogarithms, but just involving kind of abstract hyperkähler geometry, I think it's already known that even for SLN, it'll be the Chern-Simons line bundle.
So every time seeing this X bundle, I mean, taking as M the modular space of X bundle, and
I think that's, yeah, I think that's right.
Okay. Thank you.
Okay, Jörg.
Hi, Andy. Very nice talk. So, of course, I'm curious to know, I mean, well, this story looks familiar somehow. So, I mean, we were talking about some line bundle on the same spaces and so on in some recent work with Pietro, Joanna. And right, so what you wrote, so what is not quite, I mean, I think sort of what is clear from the way you described it is that we must be talking about the same line bundle, right? Would you agree to?
Yes, I assume so. In fact, I meant to say that, although I ran out of time, but absolutely, I assume it's the same.
Yeah, the perhaps more interesting question is you wrote some integral formula for a holomorphic section, which then if, well, the story fits together, yeah, this is what I mean. If the story fits together, should then be something else which is familiar. It should be related to the tau function the isomonodromic tau function. Well, I plan to discuss this on Thursday, but yeah, I mean, that it has such an expression, of course, would be just fantastic. And I think this is a quite non-trivial sort of, well, suggestion or guess, or I don't know how to call it, that comes from sort of putting these two things next to each other.
Let me say one preliminary thing about this. So the thing that I called psi here is a map from this line bundle to this line bundle. It's not the same thing. It's not literally the same thing as a holomorphic section of this line bundle. Now, if you restrict over like the Hitchin section or something, like if you just set all the thetas to 0, if you work on some subspace where this bundle V is trivialized, then you get a section of V. And so for example, in this thing of, I said when I take the conformal limit and I set all the thetas equal to 0, then you can interpret that psi literally as a section. And then it also has this meaning as the generating function of the locus of Opers.
Well, however, yeah, I mean, okay, I do want to take the conformal limit in any case. So I think this in any case is necessary to make the connection more precise. On the other hand, I'm not sure I want to set the thetas to 0.
Right. So that's why I think that my thing is not the thing you're after. So I mean, I think that this.
Well, yeah. I mean, but there is a generating function, right? And well, what I plan to at least briefly mention is that the tau function, in fact, and this is not sort of my or our discovery, the tau function is related to the generating function of the monodromy map. That is something that Bertola and Korotkin and also in another language, Nekrasov, have discovered fairly recently. So there is a generating function here. And the generating function, well, okay, it's a generating function. So I mean, so on the side of, say, character variety, you can choose, well, whatever Fock-Gontrov or whatever coordinates you like. And then, of course, it has to behave as a generating function behaves under changes of coordinates. And that, of course, will automatically produce some like dilogarithm formulae and so on. So the generating function has, say, transition. I mean, this generating function has transition functions which are given by these dialogues, etc. Right? So that is kind of automatic by saying it's generating function of monodromy map. What is perhaps not so obvious, or well, depending on how you look at it, is that in fact this guy is closely related to the tau function, and that is what, yeah, was pointed out in 19, I think, by Bertola Korotkin, and then there's a variant, well, a different type of argument by Nekrasov. And so, well, so this makes me sort of relatively optimistic that maybe there are related objects here. Of course, there's probably need for clarification in many places, but maybe the picture ultimately is a very nice one.
I share your enthusiasm about this. It feels like very close to something.
Yeah, it seems close, and then maybe there's some things that, yes, I mean, that need to be discussed to tie this really together. Maybe I can offer a few more bits and pieces on Thursday, but yeah, it looks like this wants to be connected somehow, I'd hope.
Okay, thank you. I'm going to resist the temptation to get involved in this very interesting discussion because I think we deserve a break before the next talk. So if there are no further questions right now, let's thank Andy again for 2 extremely nice talks. Thank you. The next talk is at 5 o'clock. In 5 minutes.
Oh, let me unshare my thing. Yeah, I mean, of course, I was tempted to mention this dream